Compound bars. Last we were talking about compound bars when applying axial load. Today we will look on temperature stresses, still under compound bars. Let's take for example, we are having a bar. This is a bar. Then we increase the temperature in this bar. What will happen to the bar? It will expand, eh? Yes. By increasing a temperature, it will expand from this initial, it will expand from original length to a final length. So because this one, it has changed. It has a change in length due to temperature. Due to temperature change, we will be using delta L. Because that extension, it was due to temperature change. Same applies. If you reduce the temperature, it will shrink. Meaning, at the end, you will have this one, which it will be your final length. There was a change in length there. This one is your change in length due to the reduction of temperature. So, your change in length due to temperature will be original length times coefficient of expansion times change in temperature. That will be your change in length if it expands freely without being under stressed. So, should it happen that your bar, you have fixed it between two fixed walls, then there is a change in temperature, therefore this one, it will be under a certain stress. And we know that modulus is equals to strain over stress. Modulus is equals to stress over strain. So because it will be under strain, then under stress, and then you can apply the formula. So okay, this one, it expands freely because it's just a one bar. Let's take, for instance, now we have two of them. We have the first one and the second one. These two, they are fixed together. Whenever they move, they will move together. So what kind of connection is this one? Parallel connection. That's a parallel connection. So this one, this two. the original length for 1, it will be the same as original length for 2. As they are moving together, it means even the final length will be the same. The changing length will be the same. So, okay, let us take the first one is copper and the second one is steel. When you increase the temperature for both of them, you increase the temperature. Which one will expand more than the other? The steel will expand more than the copper. The copper will expand more than the steel, ne? Yes. Yes. So if these two they were not fixed together, it means the copper. If they were not fixed together, the copper it was going to expand more than a steel, meaning a steel will expand up until somewhere there. If these two they were not fixed together. But now that these two they are fixed together, meaning wherever they go together. So what will happen? This one, okay, let me draw until there. So this one, it has expanded up until there, but remember they are fixed together. This one, it has expanded up until there, but they've been fixed together, meaning wherever they go together. So what's happening here? This one as is trying to expand to this position and is going together with this one. It means this one as it expands, it will be pulling this one to that direction. Okay, they are going together. So this one, it will expand up until here. So, and this still continue to expand. So this one, it will push that one to this other direction. You understand that one? Eh? So this one, as it's trying to expand to this to this position, this one, because it has finished its expansion here due to temperature, it will also try to pull this one backwards. Do you understand it? Meaning all in all, this one is being pulled to this direction, this one is being pulled backwards. Therefore, they will end up being somewhere there. It might not be a halfway, but somewhere there. It will be our final changing length from there to there. This is the final changing length due to temperature for both of them. So what type of stress are we going to have here on the black one, number 2? What type of the stress are we going to have? Tensile. And the red one? Compressive. Yes, that's so true. Again, this one, due to temperature, it was increasing freely, but when it gets here, it has to be pulled to that other to this position. So it has a tensile. So this one, it was expanding freely, but instead of reaching this position, it was pulled backwards. Therefore, this one it will be compressive, and this one it will be tensile, the type of the stress which you will get there. Is there any question? So all in all, now, okay, is this one here, this is the original, this is the final length, they are fixed together. This is the final length. Meaning final length for first one and the final length for the second one are equal. The final length is the same. So let us check here. We said this one, it was expanding freely, which is original length times coefficient of expansion times change in temperature. When it expands freely, it reaches, it gets there. But it has been pulled backwards. When you pull, what are we using? Or what are we, what are we using to pull? Or my question is ununderstandable. Okay. What causes this increase in extension or this increase in length? Is still the temperature. It's what? It's what? Stress. It's a force. It's a force. I think this one is being pulled backward by this one. It's a force. So meaning it has increased. It has increased past this point. And again, it has been pulled backwards by a force. And we said this, it will be the change in length due to a force. For the fact that it's being pulled back, there's a change in length there due to applied force. This applied force is being applied by this one. This one is for number one. This is in nature. This one is in nature. So this is for number one. For change in length for number two. What will be the formula? Original length times coefficient of expansion times change in temperature plus x. So if you want to calculate the distance from here to here, it's either you use this formula or you use this formula. You will find your final change in length in that way. So between a copper and a bronze, which one expands more than the other? How are you going to know that here I need to substitute for bronze, here I need to substitute for copper? Sorry? In the what? The coefficient. Eh? Yeah. Coefficient of expansion. It is the one which it will tell you which one will expand more. If the coefficient of expansion for bronze is greater than the coefficient of expansion for copper, it means this one it will expand more, the bronze. You understand that one? Eh? So again, for you to know that the bar will be compressive or tensile, how will you tell? Once the bar it has the greater coefficient of expansion, eh? If this one is more and this one is less, then you can tell. If the bronze, the coefficient of expansion is more than this one, it means it's compressive. If the copper, the coefficient of expansion is less than this one, you need to compare the two. The lesser one take tensile, the stress take tensile. The bigger one, the stress take compressive. At the end, you must know those things so that when you calculate resultant stress, you will know what to do. So, okay, rewriting this one, x X we said is force over times L over AE, right? Even this here, we can say F times L over AE. The question is this force different from this force? The force is the same, ne? Yes, because the force which is being pulling forward is the same force which is pulling backwards there. So the force is the same. So, as I told you, at the end, the total change in length is the same. Meaning, when you use this formula to calculate change in length, you must get the same value as when you use that formula. The values must be the same. When they say calculate change in length, it's either you use the one on top or you use the one at the bottom. Do you understand that part? Okay. Is the equation I wrote on board correct or incorrect? It's correct, ne? Yes. The change in length, this one is equal to the change in length, that other one. So in that case, instead of writing 1, I can just say change in length original. Even if I can take this original, you know that L is original. For 1, coefficient of expansion 1, change in temperature. These two, they are connected. They are connected in parallel. Meaning the moment the other one experiences the change in temperature, both of them, they will experience the same change in temperature. Meaning the change in temperature which is here is the same as that one. Again, these two, they are connected together. Is there a way that you can increase in temperature for 1 without increasing the temperature for 2? There's no way. So meaning the change in temperature is the same. Even if I did not indicate that is the change in temperature for 1. Minus FL over AE is equals to, okay, for now let me use X instead of using this one. X is equals to L2 2 times change in temperature, delta L plus X. So if I transpose the other one, I'll be having X1 plus X2 is equals to L1 change in temperature minus L2 2 times change in temperature. I was just grouping the change in length due to force, also the change in length due to temperature. Did I transpose it correctly? Okay. So, from there, this one, let me just substitute once, is FL over AE for 1111 plus F 2L2 over A 2E 2 is equals to L1 What is it that we know about the length when connected in parallel? They're equal, right? So if they're equal in that equation, in this equation, is there something we can do? What is that? What is it that we can do? They cancel, right? Yeah, they cancel. This cancel 1, 2, 3, 4. Or you first take a common LL, then they will end up cancelling each other. That's the reason you learn mathematics, so that when you come here, you know that the L, because they are equal, they will cancel. So now this L, they have cancelled. But if it happened that here I was not having L, it means they were not going to cancel. You know mathematics better than I do. So what did you say about F1 and F2? They're the same, eh? Meaning we can take a common factor. So F, it will be 1 over A1 E1 plus 1 over A2 E2. Did I take common factor correctly from this side? Okay, is equals to. Even on this other side, I'm still going to take a common factor. And that common factor will be what? Change in temperature. Change in temperature into like that. Let us talk about changing temperature. If they say the temperature changed by 50 degrees Celsius, is that 50 change in temperature? It's not change in temperature. When they say temperature changed by, yeah? This is the change in temperature. Again, it has changed by 50. The temperature has changed by 50, meaning this is a change in temperature. If they say the temperature changed to 50, change to 50. Is that 50 change in temperature? It's a final temperature, ne? If they say it has changed from 50, is this one change in temperature? No. So if they say it has changed from 10 to 70, what's the change in temperature then? 60. If it has changed from what's the change in temperature then? 80, ne? Yes. So, yeah, do not confuse the change in temperature. That's so important. So, okay, this formula, you can mark it as an important formula which you need to understand or you need to know. There's no need for you to drive this equation. You can use this formula as it is. Once it's connected in parallel, not in series, once it's connected in parallel, you can use this formula as it is. This F, again, this F we said is the same for bar 1 and for bar 2. Meaning, once you calculate this F, you can use that this F, to calculate stress 1 with area 1, or the same F to calculate stress 2 with area 2. Meaning in most cases, you will be required to find this force, or you will be forced to find this force for you to calculate the stress, the two stresses. If they say calculate the change in length, the change in length is either you use this formula or you use that formula to calculate the change in length. Either the two, you should get the same answer. Do you understand that one, guys? Okay, let us try to solve one exercise. The origin book still not here. Because who was having the origin book last time? Eh? Oh. I can take this off, ne? When we look on the coefficient of expansions between copper and steel, which one will expand more? It's copper, ne? And what will be the nature of stress in copper? Compressive. Yes, that will be compressive. So, okay. They say a compound bar consists of a steel pipe with a cross-sectional area of what 1470 millimeters square. This is steel pipe. And a copper rod with a cross-sectional area of the rod fit inside the pipe. The rod is inside the pipe. So the rod is inside the pipe. Which connection is this one? It's parallel. So with the ends rigidly fixed together, meaning wherever they go together, both have the same length. This one, even if they did not tell, because it's connected in parallel, we already know that they have the same length. The original length of the compound bar was. Then we are given these specifications. So question number 1, they want us to calculate the stresses and the nature in copper and in steel. So we know that stress for copper is equal to force which is applied in copper over area of a copper. Same applies, stress in the steel is equal to force steel over area steel. And they see, as these two, they express the same temperature, the other one is pulling the other one, we end up having this force being equals to this force. So meaning here, even if we did not indicate that's the force of a copper and the force of a steel, because that force is the same. What we need to do now is to calculate the force, which the formula is F, the one that we just derived, over A, S, or C, doesn't matter, C plus 1 over AS change in temperature. This one's what? C, ne? C minus S, copper minus steel, the bigger one minus the smaller one. So, I guess we are given everything for us to substitute. We can just substitute and find the final answer. It's 1 over, what is area C? 1,000? 490. What is it? The first one, I see this one. And the second, what is the second one? On the left, number 3. 4. Is this one? So this one is for a copper, ne? So if it's for copper, what do I substitute down there? 4 90 times what? 10 to the power negative? The power negative 6. Sorry? Yes. Sorry? Not 3. Why 6? Okay. Let me talk your language. If you have 490 millimeters and you want to convert this to meters, what do? You divide by 1,000. What to get on that one? What is M times M? M times M is meter square, right? What is millimeters times millimeters? Millimeter square, ne? This millimeter square. So meaning here we are having this one. Okay, let me put this one in brackets. We are having millimeters times millimeters to give us millimeter square, right? So now you have divided by the first millimeters. So you do not convert the other millimeters. You do not convert. You only can convert 1 millimeters. This one is just to convert millimeters. What about the other millimeters? So meaning even the other millimeters you need to convert by 1,000. And what does this give you? Doesn't it give you 1 million? Eh? Yeah, 1 million. Mathematics, when you take it on top, you do, when you write this in exponential form, is it not this one? Sorry? But here, when you write it in exponential form, it will be 490 over 10 to the power 6. So when you take this as numerator, it's negative, ne? So do you understand that one? Okay, I want to see if you understand that one. Convert this one. 490 centimeters square. Convert it to meters. Times 10 to the power? Yes. Times 10 to the power negative 4. 490 times 10 to the power negative 4. It's correct. Is it 100,000 or is it 10,000? Yeah, 100 times 100. Yes, 100 times 100. Yeah, that's correct. So we can carry on. So, okay, we need to multiply by EC, which is 100. Exponent 9. Times 10 to the power negative 6 and exponent 9 is the same thing. But when you write it, do not write this one, write this one, so that everyone can understand. You may find that I'm the only one who understands this. So, okay, plus 1 over, I guess now you understand, it's 1470 exponent negative 6 times 2 exponent negative 9 is equals to change in temperature. Do we have change in temperature? Did I skip it? Let me check. Oh, they say calculate. They said number A, the magnitude and the nature of stresses in the pipe and rod if the temperature of the compound bar is raised from 20 degrees to 100 degrees Celsius. Do you understand that one? Yes. The temperature has changed from 20 degrees Celsius to 100 degrees Celsius. What will be the value of change in temperature? Is 80. Meaning here is 80 in brackets. Do not jump the page. This one will be 18 exponent negative 6 minus 12 exponent negative 6. So calculate your F. Calculate F. Sorry?
2016.
Final answer. Hey, you're good in that. 16 0. Is it Newton or kilonewton? Newton. Meaning in kilonewton will be 20,160 kilonewton. So remember, we were not required to calculate a force. We were required to calculate a stress. So we need to calculate a stress. Therefore, you take this one, you substitute there, even the area. You also take this one, you substitute here, even the area for that one. And then you tell me the stress for copper and the stress for steel. You must also tell me the nature. Sorry? 4, 11, 4, 2, 8, 5, 7. Can you write it in meg? Sorry? Start. 0.14. Can you write it in meg? 41, 41,143 megapascal. The nature? Compressive. Then this one? $13, 714 megapascal. Nature? Tensile. Do you understand how to get the two natures? Okay. We are done. But before we finish, we should calculate change in length. Change in length. So your change in length, this row, these two rows, you use copper. These two rows, you must use a steel to calculate your change in length. Do you understand? Yes, calculate your change in length. The other two rows must use a steel, the other two a copper. What do you get? Oh, you're still calculating. Anything?
Says calculated change in length.
I want a change in length.
Only.
A final change in length. I agree we said, sorry? 1,224. This one did not get 1,22. I got 0, something in meters. 0,8 something.
Yeah.
What did you get?
8,743.
Which one were you using?
Still.
We're using a steel.
Yeah.
You got
8,743 times 10 to the power minus 4.
843.
8,743.
There's 3 here, comma.
8,743.
8,73.
743.
Okay, let us start afresh. I'm close to us. It's 8.743.
Charge set to the power minus 4.
Others? This one, we're using this one. It's 8, 743 times 10 to the power negative 3, negative 4 meters. Let me check here. I will come back to you and explain a bit. This one they got 0,874 millimeters.
Yeah. That one is made. So you print it out like 1,000.
Oh yeah, because here is times 10 to the power negative 4. Ne?
Yeah.
I told you to press engineering mode. Learn to young by this. Okay, Mamela note. We said initially we had this one, and this we had these two. We said this one it will expand up until here, and this one will expand up until here. So we said this one it will pull this one backwards. This one it will pull this one forward. Then the end it will end up there. So we said for the one which expand more, which is copper, the change in length for copper, it will be original length times coefficient of expansion times change in temperature. For copper, because expand more, you subtract x. Then, if you are using this for copper, if you are using steel, because the steel is the one which is also being pulled, you will say change in temperature for a steel is equals to original length times coefficient of expansion times change in temperature plus x, because it's been pulled forward. Do you get that one? So you see where you went wrong. Okay. So this one, the x is FL over AE. X. The F you have already calculated the goose. So okay. Yes. When you use stress, which stress? Oh, you mean for X, you use stress times L over E. It's the same formula. It's the same formula. So, okay. Let us check here. Those two stresses, you got them due to what? Due to temperature change, ne? Okay. So let's check, for instance, after we had our temperature change, and I come here and I apply a force now, axial force. I apply axial force. So the moment, let's say I come and apply axial force of 80 kilonewton. 80 kilonewton. So it means in this case, this is still a compound bar. But this compound bar, you must first calculate using a temperature change, right? The way you understood it today. Then after that, you calculate the stresses again using the applied force, what we were doing yesterday. Meaning by the time you calculate using a temperature, it means you ignore this force. The time you calculate using this applied force, it means you ignore what? The temperature. So at the end, what kind of the stress are you going to get here? It's tensile, ne? So meaning you'll get a stress of a copper, which it will be tensile. You get a stress of a steel, which it will also be a tensile. Due to what? Due to applied force. You understand that one, eh? So now you are having two stresses. You have the stress due to a temperature. You have a stress due to a force. So now we need to combine the two to get your resultant stress. When they say calculate the resultant stress, they want you to combine the two stresses due to temperature and due to applied force. So how do you combine them? Let's take can you see the copper? The copper is compressive and tensile. Meaning those two are opposite, ne? It means you will subtract. You take the bigger one, you subtract the smaller one. So if you check the steel, this one here is tensile and also this one is tensile. They are the same. It means you add the stresses to get your resultant stress. Meaning you'll be having your resultant stress for copper and resultant stress for steel out of these two. Do you understand how to calculate using a temperature? Ne? And you also understand to calculate using applied force. For instance, let us check at number 6, page 93. Number 6, page 93. It says a rigidly parallel connected compound bar consists of a steel strip 300 square millimeters in cross-sectional area and a copper strip with a cross-sectional area of 400 millimeters square. Must you understand that millimeter square? Ne? It's an area, it's just that it's written in here. The length of the bar is 400 millimeter. The bar is heated from 20 to 60 and then subjected to a load of 80. Do you understand that one? Ne? Which force is that 80? Is it this force which we have been calculating, or is it this applied force? Is the applied force, ne? Yes. Meaning, what you'll do, number 6.1, they say calculate both material, the stress due to temperature change. Meaning, when you start calculating the stresses due to temperature change, you will ignore that 80. You are going to ignore that 80. Then you calculate this force. Then after calculating this force, you calculate the stresses. Then you also indicate the nature of these two stresses. Then number 2, they say calculate the stresses due to external load. Meaning now, you are going to calculate the stresses like this one, at where you apply the load, as we were doing yesterday. Then you will get your stresses, both of them. What kind of the load is that one? They did not indicate there if it will be if it is tensile or yes. So okay, from there they say calculate the resultant stress in the copper and in the steel. So knowing the nature there, you'll be able to add the two. So number 6, it's your homework. Number 6 is your homework. Tomorrow when you come, we are going to do the correction of this homework and the one of yesterday, which you did not do.